Okay, so the beginning of the book is a lot of Algebra 2 review, like what is a function, what is domain and range. So we're going to try zooming through as much of it as we can. Like Friday's quiz might only have one problem on it over these first 4 sections, like a domain and range question. But I do feel it's necessary to hit it in detail because it's kind of that foundational understanding you're going to need for trig and all that. And like piecewise, for example, is going to come up a lot throughout the course and then calculus. So let's review. First of all, we're going to look at what some future chapters are going to hold for us. The first few chapters really are a review of Algebra 2. So primarily, and this is all in your textbook. I don't think you necessarily need to copy this whole table down unless you're like one of those obsessive note takers. Got to get it written down. But this is in your textbook. I just pulled it straight from there. But this is these types of functions. So today's topic, everything we're talking about is functions. These are some types of functions you have definitely studied in detail in previous math classes, like linear functions, quadratics, polynomials, a rational function, which is just a polynomial divided by another polynomial, and radical functions, which is just a polynomial inside of a radical, right? We will be studying them in more detail in chapters 1 and 2, but these are special types of functions specifically called algebraic functions. And so one thing we need to get a good understanding of, you've probably never actually learned this, is what does that term algebraic mean? What is the definition of algebraic? And what is the opposite of algebraic? If a function is not algebraic, what is it? Anybody know in math what the opposite of algebraic is? You might think it's an English term, like Walt Whitman and Thoreau. What were they? They were there you go, transcendental. So algebraic functions, the functions that are not algebraic are called transcendental. And so here are some examples of transcendental functions. Right? Weren't they the transcendentalists? Okay. So transcendental functions are exponentials, logarithms, trig functions, inverse trig functions, and we'll study those in detail in chapters 3 and 4, and then trig will be around with us pretty much for the rest of the year. 5, chapter 6, 7, 8, 9, everything. So what do these words mean? What is algebraic? What is transcendental? And what is the big difference? And to really understand the differences, we need to learn new types of numbers. First of all, let's review. What is the largest set of numbers you've ever learned about in your math career? Even bigger than real, you learned about the last year in Algebra 2. The complex numbers, right? The complex numbers. So far, to date, in your math career, that's the biggest set of numbers you've ever learned about. The complex numbers are a combination of what 2 types of numbers? Real and imaginary. The reals get broken down further into rational and irrational. Complex numbers are a combination of real and imaginary. So inside the complex numbers is what is relatively a very small set of numbers that we call the real numbers. Okay? Real numbers can be split into one of 2 groups, rational or irrational. Right? And then rationals, we can further specify as integers. And then there's the natural numbers, which are the positive integers, and so on and so on, right? So do we remember that? You studied that in the previous classes, types of numbers, and what is an integer versus irrational versus an imaginary? What's the difference between the set of integers and the set of whole numbers and all that stuff, okay? Well, there are 2 other sets of numbers that don't really fit in a diagram like this because they overlap. Like if I were to draw this next set of numbers, it'd be like, it'd be really hard. And you probably never learned about it. But there are 2 other types of numbers. There are algebraic numbers And then what do you suppose the other set of numbers is called? They're transcendental numbers. Okay? So algebraic numbers and transcendental numbers. What was the common theme you saw in every one of those algebraic functions? They all involve some sort of, what's the P word? Polynomial, right? Linears are degree 1 polynomials, quadratics are degree 2 polynomials. A rational function is just a polynomial divided by another polynomial. The definition of an algebraic number is a number that is a root, or more commonly you probably use the word 0, of a polynomial, specifically a polynomial with rational coefficients. So any number that can be the root of a polynomial with rational coefficients is called an algebraic number. So let's think about what. First of all, we got to understand rational coefficients. What is rational? It's the definition of a rational number. Terminates. So if you're looking at it as a decimal, it's a decimal that terminates, but not necessarily, or it's a decimal that goes on and on forever, but has a constantly repeating pattern to it. Okay? In practice, yes, those are rational numbers. The true definition of a rational number is it's a number that can be written as a nice fraction. So all of those decimals that terminate or repeat can be written as a nice fraction. By nice fraction, I mean an integer divided by another integer. Okay, that's rational. A rational number is any number that can be written as an integer divided by another integer. So therefore, square root 2, well, yes, I can express square root 2 as a fraction because it's not an integer over an integer. It's not a rational number. Its decimal goes on forever and ever, but never repeats. Okay? So let's think about that. All of the numbers that can possibly be the solution to a polynomial with rational coefficients. Somebody blurt out a number, any number. 4. Seriously? 4? Oh, okay. The number 4. Can I create a polynomial that has rational coefficients that has 4 as a root? Yeah, here's a very simple one. How about that linear polynomial right there? Right? Is 4 a root of that polynomial? Yes. Does that polynomial have nothing but rational coefficients? Yeah, you got 1 and negative 4. That's great. So therefore, what type of number is the number 4? It's algebraic. It's an algebraic number. It's an integer. It's rational. It's real. It's complex. But we can also call it algebraic. Blurt out another number. What's that? 87. Because I can create a polynomial that has 87 as a root, and that polynomial has rational coefficients, 87 is algebraic. In fact, isn't this pattern make it quite obvious that all numbers of what type also happen to be algebraic? It's rational. Not all real, but all rational numbers. For example, x plus 2/3. Is that a polynomial with rational coefficients? Yes, and what is the 0 of that polynomial? Negative 2/3. So positive whole numbers, negative whole numbers, positive fractions, negative fractions, they can all, excuse me, very easily be written as the root of a polynomial, so they are all algebraic numbers. Now let's get a little bit more complicated. Let's look at x squared minus 3. Is that a polynomial with rational coefficients? Yes. The coefficients are 1, 0, and negative 3. Those are rational. So therefore, its roots will be algebraic numbers. What are the roots of that equation, of that polynomial? Yeah, I got square root 3 and negative square root 3. So here's one of the interesting things. These are numbers that are actually irrational, but yet they are algebraic. Interesting, okay? Not all algebraic numbers aren't the same as rational. Yes, all rational numbers are algebraic, but there are a lot of irrational numbers that are algebraic as well, like lots of radicals. Cube root of 5, okay? The square root of the x plus to the 5th root. I mean, you can make all kinds of algebraic numbers. So the question now becomes, then what are transcendental numbers? Anybody think of one? You know a couple. Pi. Pi is what we call a transcendental number. You cannot create a polynomial that has rational coefficients that has pi as a root. I mean, I could create a polynomial, but does that polynomial have rational coefficients? No. Okay. So pi is called a transcendental number. There's another. It's actually my favorite number in the whole world. You learned about it last year. E. Everybody remembers pi is 3.14, blah, 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 blah. What's E? 2.7, 1828, 1828. Here's an easy way to remember it. 2.7, you ready for this? Andrew Jackson. Year he got elected president. 1828. I actually had a professor who was like, hey, I got a trick for you so you can always remember what E is. 2.7, Andrew Jackson. I'm looking at it like, I don't know what year Andrew Jackson got elected president. That doesn't work for me. But I thought, it's still kind of cool. So years later, I'm teaching, and I said, hey, here's an easy way to remember E. It's 2.7 Thomas Jefferson. And I think I got by with it like a year. Nobody caught it. And like the second year, somebody's like, what? No, E is 2.71828, and Thomas Jefferson was way before 1828. I was like, really? I'm looking like, well, who was it then? So clearly that little trick doesn't work for everybody. But yeah, now you'll never forget I'll never forget when Andrew Jackson was elected president. 2.7, 1828, 1828, but then it never repeats after that. It's irrational and it's transcendental. Now, the interesting thing is, notice how all these radicals turned out to be algebraic, but there are lots of transcendental numbers, like, let's take the function sine. Somebody blurt out a number, any number. 28? All right, that works. If I were to find the sine of the number 28, so get the calculator out, sine of 28, nasty decimal. It's an irrational number. Excuse me, goes forever and ever, never repeats. But that number is most likely also transcendental, not algebraic. You cannot create a polynomial with rational coefficients that has that as a solution. Okay? Hence the reason we call this a transcendental function, sine. What about the log base 12 of 15? Right? Log base 12 of 15. Log base 12 of 15 is 1.089799571. That is also a transcendental number. So these transcendental functions, sine, cosine, tangent, trig functions, logarithms, they often involve transcendental numbers, right? If you plug nice numbers in, it's probably going to output transcendental. Not always. In fact, if you plug the number pi into sine, it outputs 0, which is not transcendental. So it's kind of interesting how they don't always output transcendental numbers, but lots and lots of them are transcendental. Okay? So transcendental functions will be one of the big focuses of later this semester, algebraic functions. But today's lesson is just about reviewing functions in general. What are functions? Have you ever learned about algebraic numbers and transcendental numbers before? There's another really, really cool result of this. Has anybody ever heard of compass straight edge constructions? So the idea is if I start with 2 points, the point 0, 0 and the point 1, 0, using nothing but a compass and a straight edge, not a ruler, just a straight edge to draw lines, what other points can I construct, right? And so there are rules where you can, like, whatever points are constructed, you can use those to set the radius of your compass, and then you can draw another circle. And anywhere circles overlap, anywhere they intersect, are new points that are constructed. And then you can draw a line through those points and draw another circle, and anywhere those intersect are new constructed points. Well, points that are constructible are algebraic. Points that are not constructible are transcendental. No matter what, you cannot use a compass and straight edge to create a point that has e or pi as one of its coordinates, or has a length of pi. It's impossible. Mathematicians tried it. They tried it forever, and they couldn't figure it out, and then finally somebody proved that you cannot do it. It's interesting. Oh, it's complicated. Look it up. At Ohio State, you can take a class called Math 549. Actually, I don't know what it's called anymore now that they're semesters. But that is where you prove E and pi are transcendental. It's called field theory. Pretty good. No, it's not Math 549. It's 582. It's a good class. I recommend it. It's good. A lot of people major in math. Math is one of the more common pre-med and pre-law majors. Something to look into. All right. Non-elementary functions. The big one we want to focus on is the piecewise. How many of you remember learning about piecewise functions in Algebra 2? Good. This has been making me happy all day. I've seen so many hands about piecewise, and historically that has not been the case. Our Algebra 2s have not covered them, so apparently the secret was making me not teach Algebra 2 anymore. Getting Marple and Hutchison in there. Somebody called Hutchison the bomb earlier. No, she explodes awesomeness apparently. Okay. So piecewise functions. There's also the absolute value function. Mostly we do absolute values of linear functions, so just a b, right? But you can do absolute values of other things, and it makes the shapes all funky looking. There's also the greatest integer function. You may have seen it in Algebra 2, but you probably spent such little time on it that you forgot it. I don't even know how much time we're going to spend on it this year, so you'll probably not remember it next year. But the idea behind the greatest integer function is this weird little symbol. I don't even know what that is. But if I put a number, somebody give me a decimal number, any decimal number.
Decimal or?
Decimal.
Oh, okay. 3.14.
3.14 sounds great. Okay. So if I take the number 3.14 and I input it into this greatest integer function, the function will output 3. If I take the number 3.7 and input it into this function, it outputs 3. If I take the number 3.9 and input it into this function, it outputs 3. Basically, what the function does is it rounds numbers down. That's all the function does. Any number that goes in, round down to the nearest integer, and that's what it outputs. It gets a little bit tricky with negatives because if I plug negative 2.1 into this function, what does it output? Negative 3. You have to go down to the next nearest integer. So when you graph this function, imagine what that would look like. All these numbers get plugged in and it outputs 0, and then all these numbers get plugged in and it outputs 1, and then it ends up looking like stair steps. We call it a step function. Does anybody remember seeing that in Algebra 2? Yeah, I don't even know if we'll see it this year at all. Let's talk real quick. I don't know when I made these notes, but apparently I was in a really goofy mood. Yeah, right. Why not? Let's talk about lines. Here's my philosophy on linear equations. I don't feel it necessary to go over linear equations a whole lot because you have probably spent weeks on it in Algebra 1, weeks on it in geometry, days on it in Algebra 2. And it is the type of thing that when you need to write the equation of a line, it will come back to you very quick, right? If I were to ask you right now, what is the equation of a line that goes through the point 2, 5, and has a slope of 7, who feels like they'd be able to do it and get it right now? Right? And who feels like they would mess it up? Oh, nobody wants to admit it. But given enough time, it'll come back to you really quick and be a piece of cake. How many feel like you need to spend a couple weeks on it? That's a good answer. So we'll just go over stuff real quick. Linear functions. First of all, the concept of slope, rise over run. You got y2 minus y1 over x2 minus x1, right? Everybody remembers that? Then we've got the slope-intercept form of an equation. What's the slope-intercept form of an equation? Y equals mx plus b. So in order to write the equation of a line in slope-intercept form, you have to know what two pieces of information? You have to know m, which is slope, and you have to know b, which is the y-intercept. Okay? So if I say, what's the equation of a line that has a slope of -2 and goes through the point 5, 3? Is 5, 3 a y-intercept? No. So therefore, can I use that form of a linear equation? And the answer is actually yes, you still can. No reason it's not, right? You plug -2 in for m. What do you do with the 5 and the 3? You plug them in for x and y. So you're going to have 3 equals -2 times 5 plus b, and then you just solve for b. b equals 13. Bam. So you have the equation y equals -2x plus 13. Wow, that didn't take much work, right? But, of course, it's math. We have to make it more complicated than it needs to be. Somebody along the way decided they were going to create a new form of a linear equation called the point-slope form. Because they felt like mx plus b was too limiting. How often are you given the y-intercept? Hardly ever. So why don't we make a new form of the equation where you plug in that point you're given, 5, 3, you plug in the slope, and then boom, you've got the equation of the line. You don't have to do any solving and rewriting your equation at the end. I personally think it's overkill. And so therefore, I recommend, why don't we go for it? Satirically, why make the point-point formula? Why not? Given 2 points, just plug them in. And then hopefully you'll see when we try to do that how that's kind of ridiculous. But let's look at the point-slope formula and see, is it worth it? Is it worth learning a new form for a linear equation when really mx plus b is good enough? And here's how the point-slope formula works. It actually is the slope formula. That's all the point-slope formula is. It's the slope formula. Now here's the thing with the slope formula. Aren't we plugging things in for x1, y1, and plugging something in for x2, y2, and then we're finding out what the slope is? Well, point slope is a little bit different. I only know one point, but I also know the slope. So that second point, x, y, that represents our variables, x and y, the variables that represent the entire line. So if we rewrite this slope formula as m equals y minus y1 over x minus x1, so now x1, y1 is the point, m is the slope, x and y are the variables that we're going to have in our equation. And then if we just manipulate this, like multiply this denominator over, so that I have m, x minus x1 equals y minus y1, maybe reverse it a little bit, you have what math textbooks like to call the point-slope equation of a line. Now, how many have learned point-slope? Yeah, not many. You don't need it. When I taught, even when I taught honors algebra 2, I did not teach it. I just taught mx plus b, because you never need point slope. Now, if you find yourself writing a ton of equations of lines, It is efficient. It is where all you know is a point and a slope. And in calculus, that is one of the things you do. A goal in calculus is writing equations of tangent lines. And all you know about that line is the point it goes through and its slope. So you might want to practice point slope. It is pretty nice. Let's do that same problem again. What was it? A slope of -2. And what was the point it goes through? 5.3. But let's use the point slope formula instead. So this is going to be y minus 3 equals -2 x minus 5. And I'm done. That's the equation of my line. That's it. So definitely less work, right? Now, there's only one problem. Is that usually how we write our final answer for the equation of a line? No, but is that a valid equation for a line? Absolutely. Absolutely. But we would still probably write it in mx plus b form, distribute that 2, add the 3 to the other side, and there's our -2x plus 13. Okay? The thing is, that is a valid equation of a line. That's great. The mx plus b can't do that for us. It requires we do a good amount of work. Okay? And so sarcastically, I recommend we create ourselves. I've never seen it in the textbook. We can copyright this. It can be published. Called the Drambolian point formula. Shall we create a point formula for a line? So if you're given 2 points, you just plug them in, boom, equation of a line. What do you think? Gonna do it? No, that's not. Okay. Does anybody feel like we need to go over lines in any more detail? Good. Boom, there you go. We're finally at a point in your math career where we can cover something like equations of lines in 5 minutes. Let's talk about functions. That's really what today's lesson is all about. Functions, domain and range, and different types of functions, and just reviewing everything we know about functions. We will slow down heavily when we start talking about compositions of functions, and especially when we start talking about inverse functions. Whole days on those topics. But let's see if we can remember as much as we can about domain, range, and all that good stuff. First of all, what is a function? So let's say I have a set of numbers. We'll call this set A, 1, 3, -4, 7. Maybe over here we have set B. It's got 0, 2, -3, 6, 11, like that. A function is a relationship. I'm going to relate the numbers in set A to the numbers in set B. Somehow those numbers are related to each other. Okay? And it's a mapping. The number in set A maps to a corresponding number in set B. So maybe the number 1 corresponds to the number 0. Maybe 3 maps to the number 6. -4 maps to 2. And 7 maps to 11. Okay? What I want to know is this relationship I've just created between these two sets a function? And in order to be a function, every number in set A can only point to one number in set B. So what do you think? Is this a function? Yeah, absolutely. How about this one? How about if I change it? What if I take 3 and have it point to 2? Is that a function? Okay, this is meant to be my trick question. It is a function. Some people say no. What is the reason some people want to say no, that is not a function? What's the glaringly different thing about this relationship that makes people want to say, I don't know, that might not be a function? Right. Right. The rule is each input can only have one output. Well, they see an output that has multiple inputs pointing to it, but that's okay. Because if I input the number 3, what does the function output? 2 and only 2, one output. That's great. If I input the number -4, what does the function output? 2 and only 2. That's great. I don't care if multiple inputs. output the same thing. They're outputting something definitive, right? There's no guess. What if we change it so that it's this? Is that a function? No. Now when I input the number 4, what does the function output? 2 or -3 or 2 and -3 or, that's not a function. Okay? My favorite example of a function is a food vending machine. Right? Because, well, I love food, particularly chocolates. And I love math. Better than that. A vending machine is a function. Now, one thing we didn't talk about, what is the domain of a function? What is the definition of domain? All of the inputs. What are all of the things you are allowed to input into a function? What is the range? All of the outputs. So, what is the domain of a candy vending machine? Money. And what is the range? Food or candy. So one of the input-output pairs, one of the mappings could be 75-cent Snickers, right? The input 75 cents, output Snickers. The other could be 75 cents Mounds. Now I got a problem with that. Because if I go to that vending machine and I put 75 cents in, I bet you get a Snickers because Mounds are disgusting. So what's the problem? Is that a function? No, you've got the same input, 75 cents, outputting different things. Not a function. So where did we mess up? Yeah, the domain, yes, we put money into the vending machine. We physically input, but we don't mathematically input money, right? The money is just to kind of turn the machine on and let you buy something. Make sure you're not, like, stealing. What is the true input into this mathematical function? It's the code you have to type in with the button, right? Snickers is A3, and Mounds is probably something like B5. Okay? You input the same amount of money, but the true input of the function is the code. Okay? Now, could Snickers be so popular that they have to fill 2 different columns with it, and so you have A2 outputting Snickers as well? Yeah, absolutely. Still a function. That's great. Same output, different inputs, doesn't matter. That's a function. But what if you discover, you buy a Snickers, and it comes out like it's gross. Something's wrong with it. Mold and just gross. And you want to find out, where did that Snickers come from? Where are the defective Snickers? So you try to create an inverse function, right? Where you put Snickers in, it tells you what code gave it back. Clearly this vending machine here does not have an inverse that is a function, right? Because of that double mapping. So that is still something you want to be aware of. Yes, this is a function, but its inverse would not be a function because of this. But we'll focus on that later this week when we talk about inverse functions. And who would use that function anyway? Let me give you a Snickers and you give me back a key code combination to type in. Some sucker, that's what I say. I'm going to create one, an inverse vending machine function. You put in a Snickers and it just writes on a screen like, A3, have a nice day. Somebody would use it, I know it. Okay. That is a great idea. That is a gold mine right there. Okay. So, all coming back to you, what a function is, domain and range, all that good stuff? Good. Let's do an example. Let's do an example of a function. We're going to analyze this function. This is an actual example from your book. It wants us to just plug -1 in, plug 0 in, but I want to analyze this function in great detail, really give it a great analysis. I want to graph it. I want to analyze its domain, its range, It's a piecewise, it's great practice. Maybe talk about function notation, right? So a lot of people mess that up. And then maybe we'll answer the question it's actually asking. So here's how piecewise functions work. What is the purpose of mathematics? What is the purpose of learning about functions and how to graph functions and how if you input something, learning what it outputs? Why do we do all this? Because you use it in the real world, right? You model, so modeling real life examples with functions, and you use those functions to solve, to find the answer to your real life problem, okay? Is there usually one simple, nice function that can model a real life situation perfectly? No way. Absolutely not. Let's say I was going to take a cat up in an airplane and kick it out the door. Because nobody really likes cats. I don't, so nobody else does either. So, I'm teasing. I would never do that to a cat. Dog, maybe. But I want to model how fast that cat is plummeting towards the ground. Okay? Does anybody know what type of equation would model the position of the cat relative to the ground? Keeping in mind, gravity is a constant acceleration. It's actually a parabola, right? You would actually see a parabola like this, okay? But what does that not take into account? What would actually happen if we kick a cat out of a plane door? Yeah, so it wouldn't be a perfect parabola like that. But let's say we froze it first. Trying to make this as mathematical as possible. In a nice aerodynamic ball. This is horrible. But no, what happens to things when they fly through the air? Terminal velocity. And so therefore, is it experiencing a constant acceleration throughout its entire flight? No. So what you would actually see is, you see a curve for a while, but once it reaches terminal velocity, it is linear. Okay? So, in real life, bacteria growth is a perfect example. How does bacteria grow? Keeps splitting in half, splitting in half, and so therefore its growth is exponential, 2 to the x. But does bacteria actually grow forever, 2 to the x? I hope not, because if it did, within weeks it would cover everything in the world. Literally, it's amazing exponential growth. What happens is, take a petri dish bacteria, put a little bacteria in there, it grows exponentially. Eventually, the population of bacteria gets so big, the nutrients in the petri dish and the space, the environment can't support that size anymore, and so bacteria start dying at faster and faster rates. The bigger the population is, the faster the rate of death is. And so you end up with this nice exponential growth at first, and then it kind of levels off at its what's called the carrying capacity. Okay, and so it's very, very important. I want to create one function that models the entire situation, but I need the model, the function have individual pieces that are of different types of graphs. So piecewise are very, very important, especially if you're using a piece of software that models real-life science situations on a computer. They'll want one function, but it's got to be piecewise. So here's an example of a piecewise. This is a single function. Actually, I don't know for sure if it's a function. Let's graph it and see. It's got 2 pieces. Okay? The way the pieces work is we have a condition. If the input is less than 0, use this rule as the output. If the input is greater than or equal to 0, use this rule as the output. Well, let's look at that first rule. If you were to graph that, what shape is it? Parabola. Okay? Specifically, it's a normal, what we call a parent parabola, that you just shift up 1 unit, right? Take your parent parabola, shift it up 1. Beautiful. But I'm not going to draw the whole parabola. I'm only going to draw that parabola to the left of 0. Right? Then let's look at the second piece. What shape is that? It's a line, and by definition a line goes forever and ever and ever in both directions. Well, I'm going to draw that line, but I'm not going to draw all of it. I'm only going to draw it to the right of 0, actually including the point at 0 as well. So you could argue that that piece is actually what shape? Back to your geometry days. A line segment stops, and it has a starting point and an ending point. This has a starting point but goes on forever. We call it a ray. Right. So it'd be more like a ray. Now, could I word the condition in a way that it has an ending point as well? Say, for x greater than or equal to 0 and x less than 9? Yeah, and then it would be a line segment. But this isn't. It says to the right of 0. So what does this look like if we were to graph it? Let's get some graph paper here. Oh, smaller graph paper. Throw some axes on here. Yeah, that looks good. What's a good color? Blue sounds great. Okay. So let's start with this parabola. What's the first point you would graph in the middle of this for the parabola? I would plot the point 0, 1, except is the point 0, 1 actually graphed? No, right? It's less than 0, not less than or equal to. So I'd put a little open circle right there. Like that. Oh, nice. But the Wii remote's resolution is not that great. I tried this one last year. I thought this is such a great idea. I'm going to draw a straight line. Look at that. It's kind of cool, though, because you can clearly see, because of the resolution of the Wii remote camera, it's jumping from pixel to pixel. Kind of fascinating. Okay. So we've got this open circle 0, 1, and then I'm drawing this parent parabola going to the left. So I think it's going to go through this point, and then probably left 2, up 4, so probably up here. And you don't have to be too exact with it. But there you go. Right? And then we've got this line. It has a y-intercept of -1, and that is a closed dot because of this equal sign. And it has a slope of 1, and it's going to go off to the right. Shabam. Is that a function? When looking at a graph, how do you determine if something's a function or not? Vertical line test. Are there any vertical lines that cross this graph more than once? You know, potentially in the middle, but because that circle is open, it only crosses once, right? So yeah, that's great. That's a function. Vertical line test. Beautiful. What is the domain of this function? What's that? I thought I heard someone. Say it again? Yeah, it's all reals. It's kind of weird. It looks like in the middle, because of this jump, there might be a number missing from the domain, but there isn't. 0 is in the domain. Whatever number is slightly to the left of 0 is in the domain. Right? It's up here. Any number to the right of 0 is in the domain. So yeah, the domain is all reals. That's great. What is the range? The range is going to be -1, included or not? Yeah, so is everybody familiar with interval notations? We use that square bracket. Okay. You always use parentheses for infinity because you can't include infinity. You can't equal or be infinity. All right? That's one of the reasons Buzz Lightyear's an idiot. Beyond infinity? Come on. Okay? So does that make sense? And then the question asked, what is f of -1? Oh, all right. Have a good one. No homework.